be quiet. Okay, so we will continue on learning how to describe relationships between two numeric variables. We see that what we've covered so far is that in describing a relationship, the things we want to talk about are the shape, whether it's linear or nonlinear, the direction, whether it's positive or negative, and the strength, strong, weak, or something in between. We also want to make sure that we are describing this in the context of the data. Okay, so in these examples, I just had generic scatter plots that did not really have variables labeled or variables mentioned, but we did have a couple examples where there was a context to the data. So we said, we had the example where we were looking at people's heights and weights. So in that relationship, we would say, if we look at people's heights and weights, we would see a linear relationship that is positive, meaning taller people in general weigh more than shorter people. The relationship is probably not going to be very strong, but it will also not be very weak. It will probably be a medium or moderate strength relationship. Now, all of these terms of strong or weak, these are relative terms. So it depends on the other data sets or other relationships that you are looking at to decide whether something has a strong relationship or a weak relationship. In chapter 3, going back to chapter 3, we said when describing a numeric variable, we want to mention center, shape, and spread. And for things like the center and the spread, we had summary statistics, such as the mean, the median for the center. We had summary statistics for the spread, like the standard deviation, and the IQR, and the range. The point of those summary statistics was rather than to say there's lots of spread or there's little spread, we could actually assign a number. And a large value would indicate lots of spread. A small number would indicate small spread. And that was the reason why we have these summary statistics. That's good, right? We have the same type of thing for describing linear relationships. We have a summary statistic called correlation. And sometimes this is called, by its full name, the correlation coefficient. But if someone says this is the correlation, they're referring to the correlation coefficient. It's the same thing. Okay? So the correlation or the correlation coefficient is a summary statistic that's used to assign a number to describe a relationship between two numeric variables. Okay, so this is So in this context, the correlation serves the same purpose as all of these other summary statistics that you've learned. That purpose being describing something with a number. By understanding those numbers, we can understand, we get an idea of what the relationship looks like. Okay, it serves the same purpose, but of course, the function, what it does, is very different. So the correlation coefficient uses the symbol or letter R. Okay. You guys remember what is the symbol that we use for the mean? The mean x bar. The mean is x bar. What is the symbol or letter that we use for the standard deviation? S. Okay? Or SC, I guess. The symbol that we use for correlation is R. R can be any value between 1 and -1, inclusive. If R is positive, so that means it's anything between, 0.001 all the way to positive 1. So if R is positive, it means the relationship is positive. Are there questions over there? Good. If R is negative, then the relationship is negative. If R is close to 0, then the relationship is weak. And if R is far from 0, which means R is close to 1 or -1, then the relationship is strong. Yes?
So in the first one, there with the straight line, is it 1?
Yeah. So in this example, where we have a very strong relationship, okay, R would be very close to positive 1. Okay? If all the dots were exactly on the line, then R would be positive 1. Because the dots aren't exactly on the line, R is probably equal to 0.99. So very close to 1, positive, very strong. The dots aren't exactly on the line, so it's not 1, maybe 0.99. Yes?
And the one below would be like -68 or 70 something?
Yeah, and over here, the relationship is negative. It's not super weak, okay? It's much weaker than this one, but maybe R is negative 0.5. This is just a ballpark guess, okay? So this would be R is equal to 0.5. I'm just making these numbers up kind of as a ballpark figure. I'm not expecting you to look at some scatter plot and know exactly what R is. But if I gave you some values and I asked you to match them, you should be able to do that. Okay. And over here, if we have something, let's say you see a scatter plot that looks like this, what would you say R is here? Yeah, we would have no relationship, so R would be equal to 0, or no relationship. Okay, the relationship is neither positive nor negative, and R reflects that. 0 is neither positive nor negative. There's no relationship.
Then it would still be considered strong.
No.
Because it says if R is, oh, never mind.
Okay, so if R is close to 0, then the relationship is weak. Obviously, if R is 0, then the relationship is so weak that there is no relationship. Okay, so R is our correlation. Now, here's an important thing to remember. Correlation is a statistic, and it can be calculated no matter what your data looks like. It is only meaningful when we have a linear relationship. How can we see if there is a linear relationship? What do we have to do in order to see if a relationship is linear?
Look at them on a scatter plot.
We have to make a scatter plot. Okay? If we don't make a scatter plot, we won't know if the relationship is linear or nonlinear. So we always have to make a scatter plot. R can be calculated even for nonlinear relationships. However, it will not be meaningful. Okay. Last week in chapter 3, we learned that we can calculate the mean and the standard deviation and the IQR for any sets of data. But we said for skewed data, we prefer the IQR and the median, that stuff. For symmetric data, we would prefer the mean and the standard deviation. Similar concept here in that for linear relationships, R is meaningful. For nonlinear relationships, R exists but is not meaningful. Okay? So R is meaningful only for linear relationships. To see if a relationship is linear, let's make a scatter plot. R still exists for nonlinear relationships. But in those cases, R is not. Okay, so just a quick check of our understanding. Don't shout out your answers. A, B, C, and D, and match the following correlations. match the following values of R to the appropriate scatter plot. Okay, are we good? Okay, so which one has 0.98, correlation of 0.98? C. This would correspond to graph C. What about negative 0.99? A. Negative 0.03? D. And this one would be S with B. Okay. Is it good with everyone? All right.
I have a question.
Yes. Go
Okay,
ahead.
I'm getting it right, but I'm not really understanding how I'm getting it right. It's just, I'm just connecting. Is it because the higher it is, it's just 99, right? You're,
Okay,
I'm
so
not really understanding it. I just, it's just,
The cluster is
Okay,
2, 1.
can I ask you to just be a little bit more specific with your question?
okay, for like C,
Uh-huh,
I got 99,
uh-huh.
and I knew that,
So, okay, let's look at graph C. Is this going to have a positive value or a negative value?
it would have a positive,
It would have a positive value
because it's going up,
Would
right?
it? Because it's going in that direction, yes? Okay.
And then for A, it would have
So-
a negative value because it's going down.
Correct. Now, for C, would it be closer to 1? Would it be close to 1 or not so close to 1? Huh?
Not so close?
For C?
Yeah.
Okay, what's our rule for describing strength? So for correlation, if the relationship is strong, R is going to be far from 0. And if the relationship is weak, R is going to be close to 0. Okay. So would we say the relationship here is strong or weak?
It's strong.
It's strong. How do we know it's strong?
Because it's straight.
Because there's not much scattered. And so that means it's going to be far from 0. So which of those values are positive and far from 0? The first one, 0.98. Okay, so this is, it's a positive relationship. It's a strong relationship. So we're going to pick this one. Yeah.
Why is that D? Isn't D supposed to be 0? It looks like it doesn't have a relationship.
Yeah, it doesn't look like there's a relationship, but maybe, okay, so whenever you graph data, very rarely will you have actually R equal to exactly 0, okay? So there's probably no relationship, or if there's any relationship, it's incredibly weak. And so maybe just as an artifact of the data, we have something very close to 0, but not necessarily 0. Does that make sense?
Yeah, but couldn't that just be a weak? Couldn't that just be weak? A negative weak?
So, are you saying this should be 0 or it should be?
It should be 0.
It should be 0.
Like,
Okay. And so what do I have here?
it's negative 0.03, but another rule says that if R is close to 0, the relation is weak.
Right.
So that one is close to 0.
Okay, but it's very close to 0, so it's very, very, very weak if there's a relationship at all. When we calculate R, you're throwing a bunch of numbers in there, okay? We would expect R to be 0 in this case. But in order for R to be 0, the numbers have to line up in kind of this perfect order, or perfect manner, in order for there to be absolutely no relationship. Okay?
Is there like a range of numbers that we should follow by that's below this should be?
No. It's just kind of a rule. You're just going to have to gauge something. Okay? So here's an example. Okay? And I hope this satisfies your thing. Okay. Let's say you wanted to test if a coin is fair. And if a coin is fair, it should land heads 50% of the time. Right? Okay. So let's say I flip this coin 100 times and it lands heads 52 times. Are you going to then say 52 times is more than 50 heads? That means the coin is unfair. Would you say that? Why not?
Because that's for that specific time we tested it. If you test another time, it could be a different set of numbers.
Okay. So what's going on in there is that we didn't get 50% heads. We got something close to 50% heads. Not exactly 50% heads. But it's close enough for us to say, I'm not convinced that it's an unfair coin. Okay. Right here, remember this is data. And so data is not going to be perfectly behaved. We're getting something where the relationship or the correlation is very close to 0, not exactly 0, but it's not enough for us to say, well, that means there's definitely a weak negative relationship. It's just because of the data, it ended up negative 0.03. Does that mean there's a relationship and it just happens to be very weak? Not necessarily. Is that okay? All right. Okay, so we have this. We have correlation. We have R. We know how R works. This all goes into play into what we call linear regression. And linear regression is all about forming what we call a model of data. We are trying to make a model of the linear relationship in our data. We're trying to assign numbers to this. So, whereas before we just said, is there a relationship? Well, maybe I'll let you guys write that, and then I will explain something so I'll have your attention. Okay, so before, earlier today, we said, is there a relationship between the height of people and the weight of people? And we said yes, and in general, taller people weigh more, shorter people weigh less. Linear regression would take that one step further, and we would say, if we compare two people and one person is 1 inch taller than the other person, we expect that person to weigh 7 pounds more than the other person. Okay, so we are assigning numbers to the relationship. We're saying if a person is taller by 1 inch, we expect them to weigh about 7 pounds more than someone else. I'm making those numbers up, but that's the kind of idea that we're going for. Does that make sense? Or if we were looking at the relationship between how many miles you've driven and how much gasoline is left in your car, before we just said if you drove more, you will have less gas left. If you drove less, you will have more gas remaining. Okay. Now we would further expand that, and we would say if you drove an extra 30 miles, we expect the amount of gas to be in your tank to be 1 gallon less. Okay, so we're assigning numbers to describe this relationship even in more detail. Does that make sense? Okay. And so how do we come up with those numbers? How do we fully describe this? That's what linear regression is all about. You have a question? Okay. So linear regression, we're we're taking all of this stuff that we've learned so far, and we're going expanding it further. We're applying numbers to it, and there's rules and formulas to all of this. Okay. I'm going to spare you all of the math that went into the formulas we're going to use, okay? A lot of smart people studied this stuff, studied the data, studied the, not really the data, the theory behind all of it, and they arrived at formulas for us to use, okay? And so rather than trying to explain all of the complicated math that goes into it, I'm just going to say, here are the formulas you're going to use, and we're going to learn how to use them well, okay? And if you want to know the history behind all of this, I would encourage you, it's good stuff, but it's probably beyond the scope of this course, and you would have to take a mathematical statistics class. Yes?
Will there ever be a case where
A line goes vertical. Yes, that would be a case where you have no relationship. It would be somewhat like, how many eyes do you have and how much money do you make? And we just flip the two variables around. If we said the x variable was how many eyes do you have, and the y variable was how much money do you make, then you would have a vertical line. No relationship there. So with linear regression, we're trying to make a model of the linear relationship in our data. Okay, so the line that we're going to make is a straight line, and in algebra, you learned the formula for a straight line was what? Y equals mx plus b. Okay, so in algebra, we have y equals mx plus b. This is familiar, right? Okay. M was the slope, and b was the intercept. Okay. That was in algebra. In statistics, we change things around a little bit. Okay? In statistics, we put y, and we put this thing over it, and we call this y hat. This is known as y hat. Y hat is equal to a plus bx. Okay. And in this case, a is our intercept, and b is our slope. Y hat is not y, it is our prediction for y. When you see a hat over something, it means it is our prediction or it's based on our data, not necessarily what happens in truth. Okay, so y hat is our prediction for y. And then we have the intercept, and we have the slope. And this is how we are going to model linear relationships. We are modeling them with just a straight line. To calculate the slope is equal to the correlation coefficient r times the standard deviation of y divided by the standard deviation of x. Okay, so r is the correlation, we already know that. Okay. Sy, so all you have to do, a subscript just means for this thing. Okay, so S we learned is the standard deviation. So this is the standard deviation. And the subscript y just means standard deviation of y. S of x is standard deviation of x. So we've plug in r, s sub y, s sub x. I'm saying sub y, meaning subscript y. So r, s sub y divided by s sub x to get our slope, b. And then a, our intercept, is given by y bar minus b times x bar. Okay. Yes? Standard deviation of y. If you can't see, I welcome you to come sit in a closer seat. Okay. A is our intercept. We have that over there. What is y bar?
Mean of y.
Mean of y, great. X bar is our mean of x. And what is b?
Slope.
B is the slope that we found in the previous part of the problem. So you have to find the slope first, and then you can find the intercept. Okay, so let's think of our example where we are looking at the distance traveled The distance traveled will be our x variable, and we will have the amount of gas remaining in our tank. Is our y variable. And let's say we have our data. Okay, we have x and we have y, and we said there was somebody who traveled 260 miles and they had half a gallon left. Somebody who traveled 150 miles and they had 4.5 gallons left. Maybe someone who traveled 0 miles and they had 10 gallons left. Someone who traveled 30 miles and had 8.7 gallons left. Okay? So on and so forth, with more data. Is that okay? Okay. Let's say we have a bunch of data points. I only have 4 listed up here, but let's say we had 100 data points, and we summarized all of them. Okay, we found the correlation. Let's say the correlation between our 2 variables is negative 0.85. Let's say the standard deviation for y is 60, and the standard deviation for x is 1.8. Let's say the mean of y is 150, and the mean of x is 5. Yes?
For test purposes, homework purposes, is this how it's going to be given to us, or are we going to have to find every single?
So in test and homework purposes and stuff, these will probably be provided to you, but maybe in a paragraph. And I will not have them listed out for you to make your life easy. And you will have to, well, part of statistics is applying these math concepts to real life situations, and that involves reading something and drawing information out of it, okay? If I just gave you numbers and said, here are numbers and do this to the numbers, this would not be a statistics class, it would be a formula plug-in class. Alright, so our regression equation again is given by y hat is equal to a plus bx. And we have our formulas for b and a. So go ahead and calculate b and a and plug them into the regression equation. Oh dear. Huh? I made a mistake here. I'll explain. No, keep going. We're fine. Yes.
What's our variable? Like which variable do we use? Like what's our x? The equation is y hat equals a plus bx, right? So x would be.
I'm asking you to come up with an equation for y.
Oh, just okay. Just x. Okay.
I made a mistake in the very beginning of the problem. I apologize. This technically should be y and this should be x. I apologize. I made a mistake. Okay.
You solve it?
Huh? No. These remain the same. I made a mistake over here. Okay, do we have answers? All right, what did we get for our slope?
Negative.
Negative 28.33. Is that right?
Yeah.
And then our intercept A is 8.33. Is that also correct? No?
Yeah.
Oh. Maybe
Yeah,
negative 1.3? Hang on. 291.665, I'm sorry. Okay. Alright, and I apologize here, it's the distance traveled is y and the amount of gas remaining is x, okay? So our x variable is gas remaining. And y is the distance traveled. So we are trying to predict, okay, and I know this is a little bit different from what I was saying. Based on this, by looking at the gas remaining, we're trying to predict how far someone traveled that weekend. Does that concept make sense? Okay, so what we're ending up with is we're looking at the tank, we say how much gas is left in the tank. Based on how much gas is left in the tank, we're trying to make a prediction for how many miles the person traveled. Yes?
I think, I don't really understand how you get these numbers. Can you explain?
Okay. I will explain in just a bit, but I just want to make sure this part is clear first, okay? So we look at x, meaning how much gas is left. And we are trying to predict how many miles the person traveled. Yes.
So basically with that equation is like if you asked us like you have 2 gallons, the x would be like you tell us we have 2 gallons in the gas tank.
So let me, alright,
And
we're jumping ahead here, okay? I will answer that. That's very important, but I will answer that. First we're going to get how we got the B and the A, okay? So I said this is our data, here's our x values, here's our column of y values. These are the summary statistics. We calculated the standard deviation of y, the standard deviation of x, the mean of y, and the mean of x. And we're using all of these things to get B and to get A. So all I'm doing is I'm just plugging in the values to get B. So I said B is equal to R. What is R? Negative 0.85 times the standard deviation of y, which was 60 divided by 1.8. And I get negative 28.333. Is that okay with everyone?
I get 33.3.
Am I messing something up?
I get the same thing too. Yeah. What's still the right answer?
No, I'm getting 28.333 negative.
Yeah.
You're dividing, because they're probably dividing by 18. That's
That's
what
60
you have.
divided by 1.8, you get 33.33.
Okay, 60 divided by 1.8 is 33.33.
Yeah, and you're
They're not
you're
making,
right.
they're not changing the negative to a positive. So 2 negatives to a positive, so should be adding.
If you add 2 negatives, then equals positive.
Alright, I just want to make sure we're, okay. What are you saying you're getting your answer to?
So it's 60 divided by 1.8, it becomes 33.33.
Okay.
That's multiplied by negative 0.85, I get negative 28.33.
Because did
Is
you,
that not what I wrote here?
that's true.
Negative
That's right.
if you do
28.33?
answer times,
Yeah,
then
that's
it'll
what I
give you 20.
Okay, so
But I
what's
got
the problem?
Yeah, no, that's what I got.
I have negative 28.
Right.
Wait.
But I don't know why they're getting that different.
Okay. Oh, I thought you were saying you have a problem. Okay. I'm like, let's. Alright. Who has a problem? You have a problem. What is your problem?
That when I take 60 divided by 1.8, my answer is 33.33.
That is correct.
But then you multiply by
0.85 negative.
So there's,
Ah,
you have to do R times S of Y divided by S of X.
okay. Okay, I got
He just didn't show that they're else.
The practice, yeah, or something dog.
I don't need to, okay? I'll do this just to make you guys happy, but this is unnecessary, okay? I don't need to put a dot there, alright? Huh?
But in the calculator, you have to put the parentheses or else it'll go out of order, right?
Yeah. Okay, this is why I have issues with people blindly using formulas, okay? When you see letters together in a formula, that means there's multiplication. And yes, that means when you go to the calculator, you have to know to push the multiplication button. It's fine, okay? I'll explain that, but I also feel like, okay.